Picture standing under a starry sky, gazing up at the countless pinpricks of light scattered across the darkness. Each one is a sun, a world, a mystery, some so distant their light has traveled billions of years just to reach your eyes. Yet as vast as the universe seems, it's what we can't see, the structures lurking in the shadows of space, that truly boggle the mind. Cosmic giants so strange, so unfathomable, they defy the very laws of physics as we know them. From voids so empty they shouldn't exist to walls of galaxies stretching across unimaginable distances, the universe is hiding secrets that challenge everything we think we know. What if I told you there are places out there, 25, to be exact, where the rules of reality seem to bend, where gravity twists into knots, where time itself might stutter, and where the fabric of space stretches into shapes so bizarre they seem ripped from the pages of science fiction? These aren't just curiosities, they're cosmic riddles written in the language of the universe, waiting for us to decipher them. And the wildest part, some of these enigmas are so far beyond our reach, so shrouded in mystery, that we may never fully understand them. That's the journey we're embarking on today, a voyage to the edges of comprehension, where the universe reveals its most bewildering creations. We'll unravel the stories behind these celestial anomalies, from the eerie silence of the Boots void to the mind-bending scale of the Hercules-Corona Borealis Great Wall. By the end, you'll see the cosmos not just as a collection of stars, but as a puzzle box of wonders, each one more astonishing than the last. So let's dive in, because the universe has been keeping secrets and it's time we uncovered them. Deep in the direction of the constellations Centaurus and Hydra, hidden behind the thick veil of stars, dust, and gas that makes up our own Milky Way, lurks something massive enough to bend the motion of entire galaxies toward it. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's dragging hundreds of thousands of galaxies, including our own, through the cosmos at a staggering speed of over 600 kilometers per second. Imagine a cosmic whirlpool, invisible yet undeniable, its pull reshaping the paths of everything around it. And here's the twist, we can't even see it directly. The Great Attractor sits roughly 250 million light-years away, but our view is blocked by what astronomers poetically call the zone of avoidance, a band of interstellar material in our galaxy's disk so dense it absorbs visible light, rendering everything behind it nearly invisible. It's like trying to peer through a frosted window while standing in a brightly lit room. For decades, this region was a blind spot in our cosmic maps, leaving the Great Attractor's true nature shrouded in mystery. Only with advancements in radio, X-ray, and infrared astronomy have we begun to pierce that obscuring curtain, revealing glimpses of a colossal concentration of mass. But what is it? The leading theory suggests a supercluster of galaxies, an assembly of matter so vast its collective gravity dominates an entire region of space. Yet even that might not tell the full story. Some researchers speculate there could be something even larger beyond it, a structure we've yet to identify, tugging on the Great Attractor itself. Others wonder if dark matter, that enigmatic cosmic scaffolding, is woven into this region in unexpected ways, amplifying its gravitational grip. What makes the Great Attractor truly humbling is the scale of its influence. Our local group of galaxies, the Milky Way included, isn't just drifting aimlessly through space. We're caught in a river of motion flowing toward this hidden leviathan. It's a reminder that even as we map the universe, some of its most fundamental forces remain just out of sight, pulling strings we're only beginning to sense. And if something this massive can hide in plain darkness, what else might be lurking beyond our view? If the Great Attractor is a cosmic lighthouse pulling galaxies toward it, then the Boots void is its polar opposite, a yawning chasm of nothingness so vast it could swallow thousands of Milky Ways without a trace. Stretching 330 million light-years across, this immense spherical desert is eerily devoid of galaxies, a void in the truest sense of the word. To put that scale into perspective, if you place the Milky Way at one edge, the nearest major galaxy would be so far away, its light would take tens of millions of years to reach us. It's a region where the universe seems to have skipped a beat, leaving behind a silence that echoes across the cosmos. The mystery deepens when you realize how statistically improbable this void is. Based on our current understanding of cosmic structure, regions this large should contain at least 2,000 galaxies. Yet when astronomers first mapped the Boots void in the 1980s, they found fewer than 60, a scattering of lonely islands in an ocean of darkness. It's like stumbling upon a city-sized patch of land where only a handful of houses stand, with miles of empty space between them. The question isn't just why it's so empty, but how it could form at all without violating the fundamental rules of galaxy distribution. One leading theory points to the very beginnings of the universe. In the chaotic aftermath of the Big Bang, tiny fluctuations in density may have created pockets where matter clumped together, while other regions stretched into barren expanses. The Boots void could be a fossil from this primordial era, a bubble that never quite filled in, preserved over billions of years. Another possibility is even more mind-bending. Smaller voids merging over cosmic time, like soap bubbles coalescing into one enormous emptiness. Then there's the more speculative angle. Could advanced civilizations have something to do with it? Some theorists play with the idea that a Kardashev Type 3 civilization, harnessing the energy of entire galaxies, might have rearranged matter on such a colossal scale. But let's be clear, that's fringe science bordering on cosmic folklore. What is undeniable is the void's unsettling effect on our cosmic models. It challenges the assumption that matter is spread relatively evenly across the universe, revealing instead a tapestry full of unexpected holes. What makes the Boots void particularly haunting is how it warps our perception of space. If you were inside it, the night sky would appear almost starless, just a smattering of faint, distant galaxies against an inky blackness. No bright nebulae, no galactic neighbors, just silence. It's a reminder that the universe isn't just defined by the brilliance of stars, but also by the absences between them. And as we stare into this cosmic blank spot, we're left wondering, is it a glitch in the fabric of reality or a clue pointing to deeper truths we've yet to grasp? The Hercules-Corona Borealis Great Wall isn't just a structure, it's a cosmic titan so vast it redefines our understanding of scale. Stretching an almost incomprehensible 10 billion light-years across, this filament of galaxies is the largest single object ever identified in the observable universe. To grasp its enormity, picture this. If you could travel at the speed of light, it would take you longer to cross this wall than the Earth has existed. It's a web of galaxies, galaxy clusters, and dark matter woven into a ribbon stretching across nearly a seventh of the visible cosmos, a spine of the universe itself. This behemoth wasn't discovered through telescopes peering into the night sky. Instead, it revealed itself in the afterglow of gamma-ray bursts, the brightest explosions in the universe, marking the deaths of massive stars. By mapping these bursts like breadcrumbs, astronomers in 2013 noticed an eerie pattern. They clustered along a curve spanning the constellations Hercules and Corona Borealis. At first, scientists doubted their own data. A structure this large shouldn't exist under the cosmological principle, the foundational idea that the universe should look roughly the same no matter where you observe it from. Yet here was evidence of a cosmic lopsidedness, a wrinkle in the fabric of reality. What makes the Hercules-Corona Borealis Great Wall so unsettling is its defiance of cosmic limits. According to standard models, structures larger than about 1.2 billion light-years shouldn't form because there hasn't been enough time since the Big Bang for matter to clump on that scale. Yet this wall is nearly 10 times that theoretical maximum. It's like finding a single mountain range stretching across an entire continent, except the continent is the observable universe. Some theorists suggest it might not be one coherent structure but a chance alignment of smaller filaments, like overlapping brushstrokes on a canvas. Others argue it's evidence of exotic physics, perhaps even relics from the universe's inflationary phase, when space itself expanded faster than light. Then there's the haunting implication. If structures this colossal exist, what does that say about the universe beyond what we can see? The cosmological principle assumes homogeneity, but the Great Wall whispers that the cosmos might be more textured, more uneven than we ever imagined. It's a reminder that every time we think we've grasped the universe's rules, the cosmos throws us a curveball 10 billion light-years long. And as we stare at this galactic tapestry, we're left wondering, is it a flaw in our models or a sign that the universe is far stranger and far grander than we dared to dream? Most galaxies come in familiar shapes, spirals with their graceful arms, ellipticals like glowing orbs, or messy irregulars with no clear pattern. Then there's Hoag's object, a cosmic oddity so perfectly circular it looks less like a galaxy and more like a celestial bullseye. Imagine a golden yellow core floating serenely at the center, surrounded by a pristine blue ring of young stars with nothing but darkness bridging the gap between them. This 200,000 light-year-wide enigma, discovered in 1950 by astronomer Art Hoag, defies every expectation of how galaxies should look. Even more baffling, there's barely a trace of the chaotic debris you'd expect from a collision, just a symmetrical, almost designed structure hanging in the void. How does something like this form? The leading theory involves a galactic collision billions of years ago, where a smaller galaxy punched through the center of a larger one, sending ripples of gas and stars outward like waves from a pebble dropped in a pond. Over time, those ripples could have condensed into the ring we see today, while the central core remained intact. But here's the catch: Hoag's object shows no signs of the usual violence associated with such an event. No distorted trails of stars, no leftover dwarf galaxies lurking nearby, just eerie perfection. Alternative explanations lean on the galaxy's own instability. Some models suggest that resonant waves within the galaxy's disk could have triggered star formation in a perfect circle, leaving the center untouched. Others propose that an ancient bar structure, a straight line of stars often found in spiral galaxies, might have dissolved over time, leaving behind this rare ring as a fossil of its former shape. But these theories still can't fully explain the sheer cleanliness of the divide between the core and the ring. It's as if someone drew a cosmic boundary and said, stars here but not there. What makes Hoag's object even more fascinating is how few of its kind we've found. Out of the 2 trillion galaxies estimated to exist, only a handful exhibit this pure ring structure. That rarity suggests these galaxies might be brief cosmic phases, snapshots of a fleeting moment in galactic evolution. And if that's true, we're witnessing something transient, like catching a soap bubble mid-pop. Yet the real magic lies in what Hoag's object makes us question. Is it a freak accident, a cosmic coincidence, or is it hinting at processes we've yet to understand, hidden rules of galactic behavior that only reveal themselves in the most extreme cases? Either way, this celestial bullseye reminds us that the universe has a flair for the unexpected, crafting wonders that refuse to fit neatly into our textbooks. And as we stare at its almost too perfect form, we're left to wonder, how many more galactic mysteries are out there waiting to rewrite the rules? Somewhere beyond the edges of our observable universe, something massive is stirring, an unseen force tugging entire galaxy clusters in a synchronized flow like leaves caught in a phantom wind. Astronomers call this eerie motion the dark flow, and its existence throws into question one of cosmology's most fundamental assumptions, that the universe on the largest scales should be uniform and isotropic. But the dark flow suggests otherwise. Galaxy clusters millions of light-years apart are drifting in the same peculiar direction at speeds exceeding 1,000 kilometers per second. as if drawn toward some invisible cosmic magnet lying beyond our cosmic horizon. The first hints of this phenomenon emerged from meticulous studies of the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing subtle distortions in this primordial light, scientists noticed something startling. Clusters of galaxies weren't just moving randomly. They exhibited a collective motion that couldn't be explained by the gravitational pull of any known structure within our observable universe. It's as if you dropped a handful of marbles onto a tilted table and watched them all roll toward the same unseen edge. What could possibly exert such a grip on the fabric of space-time? One daring theory points to the gravitational influence of another universe, a parallel cosmos lurking just beyond our own, its mass warping our reality like a shadow pressing against a curtain. In this speculative scenario, the dark flow would be the first tangible evidence of a multiverse, a glimpse into realms we may never directly observe. Other researchers propose a simpler yet equally staggering explanation. A supermassive structure, perhaps a concentration of dark matter or a cluster of galaxies so vast it dwarfs even the Hercules-Corona Borealis Great Wall, lying just beyond the cosmic light horizon. But there's a catch. The standard model of cosmology insists that nothing beyond the observable universe should affect us. The expansion of space should prevent any such influence. The dark flow defies this, hinting that either our understanding of cosmic boundaries is flawed, or that the universe is far more interconnected than we ever imagined. Skeptics argue it could be a statistical fluke or an artifact of incomplete data, but the signal persists across multiple studies, gnawing at the edges of accepted theory. What makes the dark flow so unsettling isn't just its scale, but what it implies about our place in the cosmos. If confirmed, it suggests we're part of something far grander, a tapestry of matter and gravity stretching into realms we can't see, governed by forces we don't yet understand. It's a reminder that the universe might not just be stranger than we imagine, but stranger than we can imagine. And as we trace the trajectories of these galaxy clusters, we're left with a haunting question. What lies out there in the darkness beyond our light, pulling us toward answers we're not yet ready to grasp? Rising like colossal smokestacks from the heart of our galaxy, the Fermi Bubbles stretch 25,000 light-years above and below the Milky Way's disk, twin towers of high-energy gamma rays glowing faintly against the cosmic backdrop. Discovered in 2010 by NASA, a Fermi Gamma Ray Space Telescope, these immense structures resemble an hourglass of pure energy, its edges sharp against the surrounding darkness. If you could see them with the naked eye, they'd span half the night sky, dwarfing every constellation. But their brilliance isn't starlight, it's the aftermath of something far more violent, a cataclysm that rocked our galaxy's core in the distant past. The leading theory points to Sagittarius A, the supermassive black hole at the Milky Way center. Imagine a dormant beast stirring from slumber, consuming a colossal amount of matter in a feeding frenzy so intense it belched out jets of energy at nearly the speed of light. These jets could have inflated the bubbles like cosmic balloons, their shockwaves accelerating particles to extreme energies. The timeline fits. The bubble size suggests they formed between 2 and 4 million years ago, a blink in galactic terms when our ancestors were just learning to walk upright. But here's the twist. There's no evidence of recent black hole activity energetic enough to explain them. It's as if we're seeing the echo of an explosion no one witnessed. Then there's the dark matter angle. Some theorists propose these bubbles might be the aftermath of annihilating dark matter particles colliding in the galaxy's dense core, converting their mass into gamma rays. It's a tantalizing idea, offering a rare glimpse into the behavior of this invisible substance that makes up 85% of the universe's mass. Yet critics argue the energy signature doesn't quite match predictions, leaving the theory in limbo. What makes the Fermi Bubbles so mesmerizing is their duality. They're both monument and mystery. On one hand, they're scars from our galaxy's turbulent past. On the other, they might be windows into physics we've barely begun to explore. And while we've mapped their outlines, their true nature remains just out of reach, a reminder that even our home galaxy holds secrets we're still unraveling. As telescopes grow more sensitive, these glowing enigmas may yet reveal whether they're the aftermath of a black hole's tantrum or something far stranger. The Sloan Great Wall looms in the cosmos like a spine of galaxies stitching the universe together, a filament of matter so vast it makes even the Hercules-Corona Borealis Great Wall seem almost modest by comparison. Stretching an astonishing 1.4 billion light-years end to end, this colossal structure is a thread in the cosmic web, woven from thousands of galaxies bound by gravity's invisible threads. Discovered in 2003 by the Sloan Digital Sky Survey, it was the largest known structure in the universe for over a decade, a title now surpassed but no less awe-inspiring. Picture this: if you could shrink the Sloan Great Wall to the size of a football field, our entire Milky Way would be no larger than a grain of sand somewhere near the 30-yard line. Its scale isn't just impressive, it's a direct challenge to our understanding of how the universe organizes itself. According to cosmological models, structures this massive shouldn't form so easily. The universe simply hasn't had enough time since the Big Bang for gravity to pull matter into such an immense configuration. Yet there it is, a galactic serpent slithering across the constellations of Corona Borealis and Hercules, defying expectations. What makes the Sloan Great Wall so revealing is its place in the cosmic web, the vast network of filaments, voids, and clusters that make up the large-scale structure of the universe. Think of it like a sponge. The dense walls are where galaxies clump together, while the voids between them are nearly empty. The Sloan Great Wall isn't just a random collection of galaxies. It's a gravitational watershed, a place where the universe's matter has pooled over billions of years. By studying its shape and distribution, astronomers can trace the hidden currents of dark matter that sculpted it, like reading the fingerprints of an invisible hand. Yet even this titan has its mysteries. Why does it curve slightly, as if bending around some unseen force? Could there be an even larger structure beyond it, tugging on its galaxies like a puppeteer? Some researchers speculate that the Sloan Great Wall might be part of a broader cosmic pattern we're only beginning to map, a single stitch in a tapestry so vast it stretches beyond our observational limits. And here's the humbling truth: we're seeing only a snapshot. The light reaching us now left the Sloan Great Wall when Earth's most complex life forms were single-celled organisms. By the time we see its current state, if we ever could, the universe will have reshaped it into something unrecognizable. It's a reminder that these structures aren't just distant curiosities, they're chapters in an epic story of cosmic evolution, written in galaxies and dark matter, waiting for us to decode their secrets. At the heart of the Phoenix Cluster, a sprawling metropolis of galaxies over 5.7 billion light-years away, a monster is feeding. Not just any black hole, this one holds the record for the fastest-growing supermassive black hole ever discovered, devouring the equivalent of one Earth's mass every second. Picture a cosmic hurricane so powerful it warps the very fabric of its surroundings, spewing out energy that could outshine entire galaxies. And here's what stuns astronomers: it shouldn't be possible for a black hole to grow this ravenous without tearing itself apart. Yet the Phoenix Cluster's behemoth laughs in the face of theory, rewriting the rules of cosmic appetite. What makes this black hole so extraordinary isn't just its size. Though with a mass roughly 20 billion times that of our Sun, it's certainly colossal, but the sheer speed of its consumption. According to conventional models, black holes hit a limit called the Eddington rate, where the radiation from their feasting pushes back against incoming matter like a cosmic fire hose fighting gravity. But the Phoenix Cluster's black hole is consuming material at nearly 5 times that theoretical maximum, a rate so extreme it's like watching a thunderstorm defy the laws of evaporation. How does it break the rules? The secret might lie in its chaotic dining habits. Instead of steadily pulling in gas and stars like most supermassive black holes, this one seems to be gorging in violent, messy bursts. Think of it as cosmic binge eating, swallowing enormous clumps of matter in irregular gulps, creating turbulence that temporarily masks the radiation pressure that should slow it down. Surrounding it is a whirlpool of superheated plasma, glowing fiercely in X-rays as it spirals toward oblivion, but the real drama unfolds beyond the event horizon. The black hole's frenzy is reshaping its entire galactic neighborhood, pumping enough energy into the cluster to halt star formation across thousands of light years. Here's the irony: black holes are often called destroyers, yet this one is also a reluctant creator. The same jets of energy that suppress star birth in some regions are compressing gas in others, triggering explosive stellar nurseries at the edges of its influence. It's a cosmic paradox, an agent of chaos sculpting order on scales we're only beginning to map. The Phoenix Cluster's black hole offers more than just spectacle. It's a living laboratory for understanding how these titans evolve. Some theorists suggest we might be witnessing a rare phase, a black hole catching up after a dormant period, like a dormant volcano suddenly erupting. Others wonder if this is how the universe's earliest supermassive black holes grew so quickly, feasting in an era when gas was abundant and limits were mere suggestions. One thing is certain: this record-breaking glutton is forcing us to rethink the life cycle of black holes. Are there others like it hidden in the cosmos, pushing boundaries we haven't even conceived? And if so, what does that mean for our theories of galaxy formation? The Phoenix Cluster doesn't just hold a black hole, it holds a mirror to our assumptions, reflecting back questions we're only beginning to ask. And as we stare into its fiery heart, we're reminded that the universe's most extreme phenomena often hold the keys to its deepest secrets. Most nebulae paint the cosmos with swirling clouds of gas, their shapes as fluid and unpredictable as smoke in the wind. Then there's the red rectangle, a cosmic anomaly so precise it looks like it was sketched with a ruler. Hovering 2,300 light-years away in the constellation Monoceros, this striking structure glows with an eerie crimson hue, its nested layers of gas and dust forming a near-perfect X-shape. At its heart, a dying star sheds its outer layers, but here's the twist: this isn't a solo act. The red rectangle's geometric precision is the work of a cosmic duet, a binary star system locked in a gravitational dance, sculpting chaos into symmetry. What makes this nebula so extraordinary isn't just its shape, but the physics behind it. Most planetary nebulae, shells of gas ejected by aging stars, expand in all directions like bubbles blown into space. But the red rectangle's central star isn't alone. Its companion star orbits so closely that their mutual gravity funnels the expelled material into two opposing cones, creating that stark X pattern. Imagine two flickering lighthouses, their beams crossing in the void, except instead of light, they're spraying gas and dust in razor-sharp jets. Over millennia, these outflows have collided, stacked, and even formed ladder-like rungs of glowing material, a phenomenon astronomers call whispering galleries, where light bounces between dust grains like echoes in a canyon. Then there's the color. The red rectangle's vivid crimson isn't just for show. It's the fingerprint of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. These carbon-rich compounds, often found in soot, thrive in the nebula's dense dust lanes, fluorescing under the central star's ultraviolet glare. It's a cosmic irony. The same molecules that give car exhaust its smell are painting one of the universe's most striking structures. But the real surprise: PAHs are considered the building blocks of life. The red rectangle might be a factory for the very ingredients that, in other corners of the cosmos, could seed planets or even biology. Yet the nebula's mysteries don't end there. Infrared observations reveal an even larger invisible structure, a vast disk of icy debris stretching far beyond the visible glow like a hidden halo. This frigid reservoir hints at a violent past, comets and asteroids shattered by gravitational tugs, their remnants now circling the dying stars. Some theorists suggest this could be a glimpse of our solar system's distant future, when the sun's death throes churn its own Oort cloud into a similar debris field. The red rectangle is more than a celestial oddity. It's a masterclass in cosmic craftsmanship. It shows how the interplay of gravity, chemistry, and time can transform stellar death into something resembling art. And as we study its precise angles and glowing rungs, we're reminded that the universe doesn't just create, it designs. The question is, how many more of these geometric wonders are out there, hiding in plain sight, waiting to redefine our expectations of beauty in the cosmos? Hidden within the swirling arms of galaxy NGC 4258, something extraordinary hums, a cosmic laser so powerful it outshines the combined light of every star in the Milky Way. But this isn't just any laser, it's a megamaser, a naturally occurring amplifier of microwave radiation, and it's painting the clearest picture we've ever had of a supermassive black hole's domain. What makes this one special? The megamaser here isn't just a chaotic burst of energy, it's tracing an almost unnervingly precise disk of water vapor, spinning around the galaxy's central black hole like a glowing vinyl record. This water vapor isn't just sitting there, it's singing. As molecules tumble in the disk, they absorb and re-emit radiation at a specific frequency, creating a signal so sharp it can be detected across hundreds of millions of light years. Imagine tuning a radio to a station where the cosmos itself is broadcasting, and instead of static, you hear pure, unwavering tones. These maser spots act like celestial mile markers, allowing astronomers to map the disk structure with pinpoint accuracy. The result, we've measured the black hole's mass at 40 million suns, not through indirect methods, but by tracking the actual motion of gas whipping around it at over 1,000 kilometers per second. But the megamaser's gifts don't stop there, because the disk is so perfectly edge-on from our perspective. Its light reaches us in a predictable way, free from the distortions that plague other measurements. This makes NGC 4258 a gold standard for calibrating cosmic distances, a ruler in the dark. By comparing the physical size of the maser disk measured via geometry to its apparent size in the sky, astronomers have refined calculations of the Hubble constant, the rate of the universe's expansion. It's like using the synchronized flicker of lighthouse beacons to triangulate your position at sea, except the beacons are water molecules and the sea is the fabric of space-time itself. What's truly astonishing is how this megamaser defies expectations. Theory predicts such disks should be turbulent, warped by the black hole's ferocious gravity. Yet here, the water vapor orbits in nearly perfect planes, as if guided by an invisible hand. Some researchers speculate magnetic fields might be sculpting the disk into order, while others wonder if we're witnessing a rare moment of equilibrium before chaos inevitably takes over. Either way, it's a reminder that even in the most extreme environments, the universe occasionally reveals pockets of startling precision. And then there's the bigger picture. Megamasers like this could be the key to solving one of cosmology's greatest headaches, the ongoing dispute over the universe's expansion rate. Different methods keep yielding conflicting results, a tension threatening to upend our models. But with more galaxies like NGC 4258 serving as cosmic calibration tools, we might finally crack the code. It's humbling to think that something as mundane as water vapor, the same molecules in your morning coffee, could hold answers to questions spanning the entire cosmos. So the next time you gaze at the night sky, remember, out there in the darkness, a galaxy is humming a tune, not with starlight, but with microwaves amplified by swirling water, etching the signature of a black hole's grip into the fabric of space. And as we listen, we're not just hearing the heart of a distant galaxy, we're decoding the universe's hidden rhythms, one precise vibration at a time. Scattered across the early universe like glowing beacons, Lyman alpha blobs are among the most baffling structures ever observed, enormous clouds of hydrogen gas spanning hundreds of thousands of light years, radiating with an otherworldly ultraviolet glow. These cosmic titans, named for the specific wavelength of light they emit, shouldn't exist under conventional models, yet there they hover, ghostly and luminous, like celestial jellyfish adrift in the blackness of space. What makes them even stranger is their timing. They appear predominantly in the ancient universe, when galaxies were just beginning to stitch themselves together. The mystery begins with their light. Lyman alpha radiation is produced when electrons in hydrogen atoms drop to a lower energy state, releasing a photon with a very specific signature. Normally, this emission is subtle, a whisper from interstellar gas, but in these blobs it's a scream. Some glow with the brightness of billions of suns, their radiation punching through cosmic distances to reach our telescopes. The question isn't just how they shine so fiercely, but why. One leading theory points to the violent births of early galaxies. As galaxies formed in the universe's first few billion years, their young stars would have bathed surrounding gas in intense ultraviolet light, energizing the hydrogen until it fluoresced like a neon sign. But here's the catch: many blobs are too large, too bright, and too isolated to be explained by star formation alone. Some stretch wider than entire galaxy clusters, their glow uniform across vast distances. This has led astronomers to consider even more extreme explanations, like supermassive black holes at their cores, funneling energy into the surrounding gas through colossal jets. Others speculate these blobs could be cosmic intersections, where filaments of the universe's large-scale structure funnel gas into glowing nodes, like water swirling around a drain. Then there's the dark matter factor. Simulations suggest these blobs might trace the hidden scaffolding of the cosmos, with dark matter's gravity pulling hydrogen into dense, luminous sheets. It's as if the blobs are glowing footprints, marking where the invisible architecture of the universe touches the visible. And in some cases, they appear to be feeding galaxies, their gas condensing into stars like dew forming on a spider's web. What makes Lyman alpha blobs so captivating isn't just their mystery, but their role as cosmic time capsules. Their light has traveled for over 10 billion years to reach us, offering a snapshot of the universe in its adolescence. By studying them, we're witnessing the raw materials of galaxy formation, the swirling gas that would eventually become everything from spiral arms to star clusters. They're a reminder that even the most colossal structures in the cosmos begin as something fragile, a wisp of gas illuminated by forces we're only beginning to understand. And as we peer deeper into their glow, we're left wondering, are these blobs the birth cries of galaxies, or the echoes of a universe still learning how to sculpt itself? Our galaxy isn't just a glittering pinwheel of stars. It's encased in an invisible cocoon of something far stranger. The Milky Way's dark matter halo is a vast, ghostly sphere stretching at least 10 times farther than our visible galactic disk, its presence betrayed only by the relentless tug of gravity on everything we can see. Imagine trying to map a city at night using only the paths of fireflies, their movements hinting at unseen streets, buildings, and alleys. That's how astronomers first deduced this colossal structure, by watching stars and gas clouds orbit the galaxy at speeds that shouldn't be possible unless something massive, something unseen, was holding them in place. The numbers are staggering. Current estimates suggest our dark matter halo weighs in at roughly 1.5 trillion times the mass of our Sun, dwarfing the combined heft of every star, planet, and nebula in the Milky Way. Yet for all its bulk, this halo isn't some solid shell, it's more like a diffuse swarm of particles, each passing through you right now without a trace. Billions could be streaming through your body every second, their gravitational whispers the only sign they exist at all. So what is it made of? The leading candidates are WIMP, weakly interacting massive particles, hypothetical entities predicted by supersymmetry theory. These would be heavy, slow-moving particles that barely notice ordinary matter, like shadowy giants stepping through fog, yet decades of searching have turned up nothing. Experiments like the Large Underground Xenon Detector hunt for the faintest recoil when a WIMP bumps into an atom, while space telescopes scour the skies for gamma rays that might betray dark matter particles annihilating each other. Then there's the alternative actions. These ultralight particles, if they exist, would behave more like a cosmic field than discrete objects, their collective mass weaving the halo's invisible web. Recent experiments like ADAMS have tuned sensitive cavities to listen for actions converting into microwaves in strong magnetic fields, a search akin to scanning a radio dial for one faint alien station among billions. But the halo's structure holds clues too. Simulations suggest it isn't smooth but lumpy, with dense subhalos lurking within it like submerged reefs. Some theorists propose these clumps could host their own dark matter galaxies, invisible counterparts to the Milky Way's satellite galaxies. Others wonder if dark matter interacts with itself more than we thought, creating complex internal dynamics we've yet to model. The most tantalizing hints might come from our own backyard. The Milky Way's outer stars show slight deviations in their orbits, as if the halo's gravity isn't perfectly symmetrical. Could this mean the halo is shaped like a squashed football rather than a sphere? Or are we seeing the scars of ancient galactic collisions, disturbances frozen in the dark matter's flow like ripples in a pond? What makes the dark matter halo so humbling is its omnipresence. It's the scaffold upon which our galaxy formed, the unseen hand that guided every spiral arm and stellar nursery into place. And as we chip away at its mysteries, we're not just studying a phantom structure, we're decoding the hidden blueprint of reality itself, one gravitational clue at a time. Stretching across the distant cosmos like a smile carved into the fabric of space itself, the giant arc is a formation so vast it forces us to rethink the very foundations of cosmology. Discovered in 2021 by astronomer Alexia Lopez, this staggering crescent of galaxies spans 3.3 billion light-years, a structure so immense it would take light, the fastest thing in the universe, nearly a quarter of cosmic history just to traverse it. To grasp its scale, imagine a thread long enough to wrap around the Earth's equator 75,000 times, except instead of thread, it's a chain of galactic islands, each one a city of billions of stars. What makes the giant arc so revolutionary isn't just its size. It's the challenge it poses to one of astronomy's bedrock ideas, the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same no matter where you're observing from, like a perfectly mixed batter. But the giant arc defies that expectation. A structure this concentrated shouldn't exist unless matter clumps together more unevenly than our models predict. It's like finding a single grain of sand the size of a mountain in an otherwise smooth desert. Theories scramble to explain it. Some suggest it's a fossil relic from the universe's inflationary period, when space expanded faster than light in its first fraction of a second. Tiny quantum fluctuations from that era might have stretched into vast density variations, leaving behind wrinkles like the giant arc. Others propose it's not a true structure but a chance alignment of galaxy clusters, like seeing faces in clouds. Yet statistical analysis shows the odds of such a perfect curve forming randomly are less than 1 in 20,000 cosmic lightning striking the same spot twice. Then there's the dark matter connection. Simulations show dark matter's gravitational web could funnel galaxies into sweeping arcs during collisions between superclusters, like beads sliding along an invisible wire. If true, the giant arc might be a snapshot of this cosmic choreography, revealing how dark matter sculpts the universe's largest patterns. But the real intrigue lies in what this means for our cosmic maps. If structures this colossal are common, our textbooks might need rewriting not just in terms of scale, but in how we define the universe's average distribution of matter. The giant arc isn't just a curiosity, it's a question mark inked across the sky, asking us to reconsider whether the cosmos is as uniform as we once thought. And as we trace its glowing contour through the darkness, we're left wondering, is it an exception or the first thread of a much larger tapestry we've yet to unravel? In the constellation Pisces, a near-perfect ring of galaxies floats like a celestial crown, its symmetry so striking it seems almost artificial. This is ZWCL 002, 4+1652, a rare and mesmerizing structure where gravity has sculpted chaos into a circle of cosmic beauty. But unlike the orderly rings of Saturn or the delicate loops of planetary nebulae, this formation wasn't born from gentle forces. It's the aftermath of a collision so violent it warped the fabric of spacetime itself. The story begins with two galaxy clusters, each weighing in at hundreds of trillions of solar masses, smashing into one another at speeds exceeding millions of kilometers per hour. Such collisions aren't just fireworks, they're cosmic laboratories revealing secrets invisible under ordinary conditions. As the clusters pass through each other, their dark matter, unaffected by the friction that slows visible matter, raced ahead, leaving the galaxies and hot gas behind. The result, a near-perfect ring of dark matter, its gravity bending light from more distant galaxies into luminous arcs around the cluster's edge, like a lens carved from shadow. This phenomenon, called gravitational lensing, turns the ring into a cosmic X-ray. By mapping the distorted light of background galaxies, astronomers can trace the invisible dark matter scaffolding with precision. The lensing effect here is so pronounced that it creates multiple mirrored images of the same distant galaxy, arrayed around the ring like reflections in a funhouse mirror. It's as if the universe itself is providing a blueprint of its hidden architecture. But what makes ZWCL 0024 ring truly exceptional is its purity. Most collision remnants are messy, asymmetrical affairs like splattered paint. This one, however, formed a near-flawless circle, a testament to the precise angle and speed of the impact. Simulations suggest the clusters must have struck almost dead center, their dark matter halos rippling outward in synchronized waves, while the galaxies, slower and more resistant, lagged behind like debris caught in a tide. The ring's geometry also challenges assumptions about dark matter's behavior. If dark matter particles interacted strongly with each other, the ring would have smeared or dissipated. Instead, its crisp edges suggest dark matter is as elusive as ever, passing through itself like ghosts in the night. Some researchers even speculate the ring might harbor clues about dark matter's temperature, whether it's cold, slow-moving, or warm, slightly faster, a debate central to modern cosmology. Yet for all its scientific value, there's an undeniable artistry to this structure. It's a fleeting masterpiece, one that will slowly fade as gravity pulls the galaxies back toward the cluster's center over billions of years. For now, though, it stands as a cosmic fingerprint, a momentary alignment of chance and physics that lets us glimpse the invisible hands shaping the universe. And as we study its luminous arcs and hidden depths, we're reminded that even in chaos, the cosmos has a way of creating perfect, fleeting symmetry. The cosmic microwave background is supposed to be the universe's baby picture, a near-uniform tapestry of microwaves left over from the Big Bang, with only tiny temperature variations revealing the seeds of future galaxies. But one patch of this ancient light doesn't follow the rules. Lurking in the constellation Eridanus, the CMB cold spot is a chilling anomaly, a region 700 million light-years wide, significantly colder than its surroundings. It's not just a statistical fluke. This frigid expanse is so extreme that standard cosmology suggests it should appear only once in every 50,000 universes. Yet here it is in ours, whispering secrets that might rewrite cosmic history. One explanation paints a picture of cosmic scars. Theoretical physicists propose this could be the imprint of a texture defect, a flaw in the fabric of spacetime itself, left over from the universe's violent infancy. Picture the early cosmos cooling like molten metal, its fundamental forces crystallizing into place. Most regions cooled evenly, but a few might have formed tangled knots, cosmic kinks that later unraveled with explosive energy. If one of these defects decayed near the cold spot's location, the released energy could have stretched spacetime, leaving behind a cooler patch in the CMB like a fingerprint on glass. Simulations show such events could create temperature dips matching observations, but textures remain purely hypothetical, ghosts in the equations of quantum field theory. Then there's the multiverse angle. Some cosmologists speculate the cold spot might be a bruise from a collision with another universe during inflation, the exponential expansion of spacetime just after the Big Bang. In this mind-bending scenario, our universe isn't alone but floats in a vast multiverse foam where bubbles of spacetime occasionally bump. Such a collision could have drained energy from our universe's edge, leaving this cooler region as evidence. It's a radical idea, but intriguingly, the cold spot's shape aligns with predictions for how a colliding universe's boundary might appear. Skeptics counter that the anomaly could simply be foreground noise, perhaps a vast supervoid of fewer galaxies absorbing CMB photons as they travel to us. Yet detailed surveys find no void large enough to explain the temperature drop, deepening the mystery. What makes the cold spot so compelling is its defiance. It refuses to fit neatly into either mundane or exotic explanations, straddling the line between measurement error and revolution. If confirmed as evidence of a texture or multiverse, it would rank among the most profound discoveries in cosmology. But even if it's just a statistical oddity, its existence nudges us to question how well we understand the universe's infancy. After all, the CMB isn't just a relic, it's a puzzle box, and the cold spot might be the first clue to cracks in our cosmic mirror. In the vast radio silence of space, some of the most enigmatic structures don't glow in visible light, they hum in wavelengths only radio telescopes can hear. Among these, none are quite as baffling as odd radio circles or ORC, ghostly rings of radio emission so colossal they could swallow entire galaxies, yet invisible to optical telescopes. Discovered in 2020 by Australia's ASCAP array, these cosmic halos defy easy explanation, floating in the darkness like echoes of events we can't yet comprehend. Each ORC spans hundreds of thousands of light years, their perfect circular shapes suggesting explosive or expansive origins. At first glance, they resemble shock waves from supernova remnants, but scaled up to galactic proportions. Imagine tossing a pebble into a pond, except the pond is interstellar space, and the ripples are 500,000 light-years wide. The problem: no known stellar explosion could produce such expansive, symmetrical rings. Even merging supermassive black holes, the universe's most energetic events, struggle to explain their scale and uniformity. One leading theory points to starburst galaxies, where frenzied star formation generates powerful galactic winds. If these winds collide with surrounding gas, they might create shockwaves that accelerate electrons, producing the observed radio glow. But there's a hitch: most ORCs don't sit near obvious starbursts. Another idea invokes fossil radiolobes from long-dead active galactic nuclear relics of jet activity that faded millions of years ago, leaving behind faint, expanding bubbles. Yet ORCs lack the twin-lobed structure typical of such remnants, their symmetry remaining stubbornly singular. Then there's the more exotic possibility: wormholes. Theorists suggest these rings could be the mouths of Einstein-Rosen bridges, their intense gravitational lensing bending radio waves into circular patterns. While tantalizing, this remains speculative. No known physics predicts wormholes would emit in radio wavelengths so distinctly. A less dramatic but equally puzzling alternative involves reverse shocks from galaxy cluster mergers, where cold gas plows into hot plasma, creating rare ring-shaped turbulence. What makes ORCs truly fascinating isn't just their mystery, but what they reveal about our observational blind spots. They were discovered not by design, but as faint smudges in all-sky surveys, lurking in data for years before someone noticed their peculiarity. Their existence hints that the universe might be filled with such structures, invisible to all but the most sensitive radio eyes. And as telescopes like the Square Kilometre Array come online, we may find these rings are just the first whispers of a hidden cosmic language, one we're only beginning to decode. For now, they hover at the edge of understanding, perfect circles scribed in radio silence, daring us to unravel their secrets. The discovery of planets orbiting the Sun like stars in our galaxy has become almost routine, but the very first worlds ever confirmed beyond our solar system defied every expectation by existing where life as we know it couldn't possibly survive. Circling the corpse of a shattered star, the pulsar planets of PSRB 1257+12 are cosmic survivors, enduring unimaginable violence to stake their claim as pioneers in the exoplanet record books. Pulsars are the universe's ultimate tombstone, spinning neutron stars so dense a teaspoon of their material would weigh 1 billion tons, their beams of radiation sweeping through space like lighthouse blades. When astronomers Alexander Wolskson and Dale Frail detected slight wobbles in the pulses of PSRB 1257+12 in 1992, they realized something extraordinary. The timing variations revealed not one, not two, but 3 planets locked in orbit around this stellar zombie. The implications were staggering. If planets could form or persist in the aftermath of a supernova, the universe's capacity for creating worlds was far more creative than we'd imagined. But how did anything survive the blast that birthed this pulsar? Supernova unleash enough energy to vaporize entire solar systems, yet here were these defiant worlds. One theory suggests they're second-generation planets born from the ashes. As the dying star ejected its outer layers, some material may have fallen back into a swirling disk around the newborn pulsar, condensing over millions of years into new planets. It's a cosmic phoenix story, with worlds rising from the wreckage. Others propose these planets were originally gas giants whose outer atmospheres were stripped away, leaving behind dense, rocky cores that withstood the cataclysm. Then there's the environment. Bathed in relentless radiation, these planets endure conditions that make Venus look hospitable. The pulsar's beams carry enough energy to strip atmospheres and scorch surfaces to barren rock. Yet calculations show one of the worlds, PSRB 1257+12c, might still harbor a thin, exotic atmosphere not of nitrogen or oxygen, but of vaporized metals like magnesium, ionized into glowing halos by the pulsar's fury. Imagine a sky shimmering with metallic auroras, the ground beneath crackling with static from relentless particle bombardment, the most haunting possibility. These might not be the only survivors. Pulsar planets could be far more common than we think, hidden in the glare of their dead stars' radiation. Recent studies suggest some neutron stars might even host rings of debris, cosmic graveyards where planets once orbited, now pulverized into glowing dust. What makes PSRB 1257+12's planets so revolutionary isn't just their resilience, it's the doors they opened. They proved planets could exist in the most hostile corners of the cosmos, expanding our search for extraterrestrial worlds beyond sun-like stars. And as we continue probing the darkness around other pulsars, we're left to wonder, if life ever did arise in such extreme environments, what unimaginable forms might it have taken? NGC 5128, better known as Centaurus A, isn't your average galaxy. It's a cosmic predator caught in the act. just 12 million light-years away, this monstrous hybrid glows with the scars of a violent past, its twisted body a Frankenstein's monster of stellar wreckage. At first glance, the galaxy's most striking feature is the thick, jagged dust belt slicing across its center like a gash. But that dark scar isn't just decoration. It's the aftermath of a galactic feast, the debris from a catastrophic merger where Centaurus devoured a smaller spiral galaxy whole. The evidence of this cosmic cannibalism is everywhere. Unlike the orderly spirals of the Milky Way or the smooth ellipses of typical giant ellipticals, Centaurus is a chaotic jumble. Young blue star clusters, stellar newborns less than 10 million years old, dot its outskirts, their brilliance contrasting with the reddish glow of older stars. These fledgling stars shouldn't exist in an aging elliptical galaxy unless something stirred the pot, and that something was likely the violent collision that reshaped this cosmic titan. The dust lanes themselves are another smoking gun, twisting through the galaxy's core in intricate patterns that only gravity from a recent merger could explain. It's as if the galaxy hasn't yet finished digesting its meal, the stellar equivalent of crumbs still clinging to its lips. Then there's the engine at its heart, a supermassive black hole weighing in at 55 million suns, one of the most active in our galactic neighborhood. Unlike the quiet beast lurking in the Milky Way center, this monster is wide awake, spewing jets of plasma over 1 million light-years into intergalactic space. These jets, visible in radio waves, are among the largest structures known, twisting and bending as they plow through the surrounding gas like cosmic fire hoses. What's fascinating is how the merger likely supercharged this black hole. As the doomed spiral galaxy spiraled inward, its gas and stars were funneled toward the center, feeding the black hole in an epic binge that ignited those colossal jets. But the drama doesn't stop there. Centaurus A's halo tells another chapter of this violent saga. Surveys reveal streams of stars' tidal tails stretching far beyond the main galaxy, the torn-apart remnants of smaller satellite galaxies it's consumed over billions of years. Some of these streams are still fresh, their stars moving in coherent groups, while others have nearly dissolved into the halo like sugar stirred into coffee. It's a galactic graveyard with each stellar ghost whispering tales of past conquests. What makes Centaurus so mesmerizing isn't just its past but its present. Even now, it's likely stripping gas from neighboring galaxies, its gravity reaching out like invisible fingers. And with its supermassive black hole still active, it's a living laboratory for studying how mergers shape galactic evolution. We're witnessing a snapshot of a process that might one day play out in our own backyard when the Milky Way collides with Andromeda. Except in Centaurus A's case, the feast isn't over, it's just another bite in an endless cosmic buffet. At the heart of the constellation Serpens, a dead star spins with such precision it could rival the finest atomic clocks, each rotation beaming out pulses of radiation like celestial Morse code. But this cosmic lighthouse, PSRJ 1719-1438, holds a secret, a planet orbiting so close it shouldn't exist at all. Meet the Diamond Planet, an ultra-dense world forged not from rock or gas but crystallized carbon, a cosmic jewel strung around its pulsar master like a pendant. This isn't the glittering fantasy of science fiction. The Diamond Planet, officially named PSRJ 1719-1438b, is the remnants of a once mighty star, stripped bare and crushed into something extraordinary. Here's how the cosmic alchemy works. The pulsar it orbits was once part of a binary system, two stars dancing in mutual orbit. The more massive star exploded as a supernova, collapsing into the pulsar we see today, a neutron star spinning hundreds of times per second. The surviving companion, now the Diamond Planet, was too close to escape unscathed. Over eons, the pulsar's gravity siphoned away its outer layers, leaving behind a core so compressed that carbon atoms, once the building blocks of a star's fusion furnace, were squeezed into a crystalline lattice. The result, a planet roughly 5 times Earth's mass, compressed into a sphere just half the size, so dense that a single sugar cube-sized chunk would weigh several tons. But the conditions here make even diamonds' vaunted hardness seem fragile. The planet's surface endures blistering heat from the pulsar's radiation, likely topping 2,000 degrees Celsius temperatures where carbon should vaporize. Yet the crushing gravity, thousands of times stronger than Earth's, keeps the material locked in its diamond form. Imagine a world where the ground beneath your feet isn't just gemstone, but a superheated, super-compressed lattice shimmering under the pulsar's relentless glare. There's no atmosphere to scatter light, no oceans to soften the landscape, just an endless, glassy plain stretching under a sky torn by radiation storms. The real marvel lies in how we found it. Astronomers detected the diamond planet not by seeing it. No telescope could resolve something so small and dark at such a distance, but by hearing its gravitational heartbeat. The pulsar's radio pulses arrive with metronomic precision on Earth, but the planet's presence introduces tiny delays as it tugs the pulsar in a slow wobble. By measuring these nanosecond variations, scientists reconstructed the planet's mass, orbit, and even its probable composition. It's like sensing a hummingbird's wing beats by the ripple they leave in a strobe light. What makes this world so tantalizing isn't just its extravagance, but its defiance. According to conventional planet formation theories, nothing should survive the supernova that birthed the pulsar, let alone remain in such a tight orbit. Yet here it spins, a testament to the universe's capacity for reinvention where destruction births not just chaos but diamonds. And as we study its grueling environment, we're left to wonder, if carbon can be forged into such extremes here, what other impossible treasures might lurk in the dark around other stellar cadavers? Deep within the spiraling arms of our galaxy, a sleeping beast stirs not a black hole or a star, but something far more insidious. Galactic superwaves are hypothetical tsunamis of cosmic radiation, theorized to erupt from the Milky Way's core in cataclysmic pulses, sweeping outward at near light speed and scouring everything in their path. Picture a shockwave of high-energy particles and electromagnetic fury, so vast it could engulf entire star systems, leaving behind a trail of atmospheric destruction and genetic chaos. While these superwaves remain unproven, their potential fingerprints might be written in Earth's own history, and our future could hang in their balance. The idea hinges on the violent nature of our galaxy's heart. Sagittarius A, the supermassive black hole at the Milky Way's center, isn't just a passive void. It's a dynamo of magnetic fields and violent outbursts. Occasionally, it might unleash bursts of energy so colossal they propagate through the galactic disk like ripples from a stone tossed into a pond. These superwaves could carry enough force to compress interstellar gas, trigger waves of star formation, and most chillingly, bathe planets in lethal radiation. Some researchers point to Earth's geological record as possible evidence. Around 12,000 years ago, the Younger Dryas event saw abrupt climate shifts, mass extinctions, and even traces of radioactive isotopes like plutonium-244, an element not naturally occurring on Earth. Could a galactic superwave have been the culprit? The mechanics are as fascinating as they are terrifying. As the wave front expands, it would ionize interstellar medium, creating a propagating wall of energized particles. Any planets in its path would experience a rapid uptick in cosmic rays, potentially shredding ozone layers and exposing life to unfiltered stellar radiation. Agriculture could collapse under mutated crops, power grids might fail under geomagnetic storms, and species unprepared for sudden genetic damage could face extinction-level bottlenecks. Civilizations without advanced shielding like ours would be staggeringly vulnerable. Yet the most unsettling question isn't just about the past, it's about the future. If superwaves are real, their frequency remains unknown. Some models suggest they could recur every 10 to 15,000 years, aligning uncomfortably with humanity's rise from the ashes of the last suspected event. Even more unnerving is the silence. Unlike an asteroid impact or solar flare, a superwave might give no visible warning until it's already upon us, its radiation heralded only by a faint uptick in cosmic noise. But here's the twist: these waves might also be cosmic architects. By compressing gas clouds, they could seed new stellar nurseries, and by delivering rare elements across the galaxy, they might even contribute to the chemical diversity needed for life. It's a paradoxical dance: destruction and creation entwined in the same energetic tide. For now, galactic superwaves linger in the realm of theory, their existence debated but undismissed. As telescopes grow more sensitive to subtle radiation patterns and fossil records are scrutinized for further clues, we may yet find proof of these phantom tsunamis. Until then, they stand as a humbling reminder. The universe doesn't just harbor threats we can see, it whispers of invisible tempests lurking in the dark between the stars. And if they're real, our survival may depend on learning to read those whispers before the storm arrives. Hidden in the constellation Monoceros, just 1,500 light-years from Earth, lurks a cosmic unicorn, not a mythical creature, but the smallest black hole ever discovered. This celestial oddity, officially named the Unicorn, weighs in at just 3 times the mass of our Sun, defying expectations for how small a black hole can be. Its discovery wasn't the result of spotting a darkened void or a telltale accretion disk. It was found by watching a lonely red giant star dance to the tune of an invisible partner's gravity. The story begins with subtle tugs. Astronomers noticed the red giant's light periodically dimming and shifting, as if an unseen force was stretching and compressing it like taffy. After ruling out planets and other stellar companions, the only explanation left was a black hole, but one so light it barely fits the category. Most known black holes fall into 2 groups: stellar mass remnants of collapsed stars or supermassive behemoths anchoring galaxies. The Unicorn bridges an elusive gap, hinting at a population of middle-child black holes we've barely begun to catalogue. What makes the Unicorn so puzzling is its formation. Traditional models suggest black holes this small shouldn't exist. When stars die, they typically leave behind neutron stars if they're under a certain mass threshold, or black holes if they're larger. The Unicorn's mass sits right on the edge, raising questions about whether it's a collapsed star at all. Some theorists propose it might be the remnants of a neutron star that grew too heavy and collapsed further, swallowing itself in a quiet implosion. Others wonder if it's a primordial black hole forged in the chaos of the early universe rather than from a dying star. Then there's the mystery of its silence. Most black holes announce their presence by shredding nearby matter, creating glowing disks of superheated gas. The Unicorn, however, is a ghost: no X-ray flares, no jets of plasma. Its content to lurk in the darkness, its presence betrayed only by the tortured orbit of its stellar companion. This stealthiness suggests there could be thousands more like it hidden in our galaxy, invisible except for their gravitational whispers. The hunt for these elusive intermediate mass black holes is more than just cosmic stamp collecting. They could hold clues to some of the universe's biggest puzzles, like how supermassive black holes grew so large so quickly after the Big Bang. If small black holes like the Unicorn are more common than we thought, they might be the missing seeds that merged to build the giants we see today. For now, the Unicorn remains a tantalizing enigma, a reminder that even our cosmic backyard harbors surprises. And as telescopes grow sharper, we may find that what we once considered rare is just the first glimpse of a hidden population waiting silently in the dark. Among the thousands of stars monitored by NASA's Kepler telescope, one stood out like a cosmic glitch in the machine KIC 8462852, better known as Tabby's star. This unassuming F-type star, named after astronomer Tabitha Boyajian, who first flagged its bizarre behavior, doesn't just dim and brighten like ordinary variable stars. It plunges into unpredictable darkness, dropping in brightness by up to 22% at irregular intervals, as if something colossal is passing in front of it. The dips aren't periodic like a planet's orbit. They're chaotic, asymmetrical, and utterly baffling. When the data first surfaced, even seasoned astronomers hesitated before offering explanations because nothing in our playbook quite accounted for what we were seeing. The most tantalizing early hypothesis, alien megastructures. The idea sprang from physicist Freeman Dyson's thought experiment about advanced civilizations building vast energy harvesting arrays around stars' hypothetical constructs called Dyson spheres. Tabby's star's erratic dimming seemed to fit. Maybe swarms of giant solar panels or orbiting habitats were blocking its light in irregular patterns. Media ran wild with the idea, but the scientific community held a more measured stance. After all, extraordinary claims require extraordinary evidence, and the universe is full of natural phenomena we don't yet understand. Dust turned out to be the leading culprit. Detailed spectroscopic analysis revealed that the star's light was being reddened as it dimmed, a telltale sign of fine particles scattering shorter wavelengths, exactly what you'd expect from cosmic dust clouds. But this wasn't ordinary interstellar dust. It had to be orbiting the star itself, likely debris from a catastrophic collision of planets or moons. Imagine the aftermath of a celestial smash-up, where pulverized rock and ice form a vast, uneven cloud spiraling inward, its clumps and tendrils casting erratic shadows. This scenario fits many of the observations, though it doesn't fully explain the star's century-long gradual dimming, another puzzle layered atop the short-term dips. Then there's the comet theory. Some researchers proposed a family of giant, fragmented comets, perhaps hundreds of them, on long, eccentric orbits around Tabby's star. As they disintegrate, they could shed enough dust to create the observed dimming. It's a compelling idea, but it strains credulity to imagine enough comets existing in one system to produce such dramatic and sustained effects. Unless, of course, something destabilized an entire comet cloud, a rogue planet's gravitational nudge, or a close encounter with another star. The truth is, Tabby's star refuses to fit neatly into any single box. Every proposed solution has holes, and that's what makes it so fascinating. It's become a Rosetta Stone for stellar mysteries, pushing astronomers to consider phenomena they might otherwise overlook. Could it be a young star still clearing its planetary debris, a mature star undergoing a rare phase of planetary system reorganization, or dare we still say it, something even more unexpected? What's undeniable is how this single star has reshaped our approach to cosmic anomalies. It taught us humility, showing that even in an age of exoplanet discoveries and space telescopes, the universe can still throw curveballs we don't see coming. And as telescopes like the James Webb turn their gaze toward Tabby's star, we're reminded that some of science's greatest leaps begin not with answers, but with the courage to say, "We don't know yet." That admission, more than any theory, is what keeps the stars full of wonder. Nestled in the Coma cluster, a gathering of thousands of galaxies 320 million light-years away, lies Dragonfly 44, a galaxy that shouldn't exist. At first glance, it's unremarkable, a faint, ghostly smudge barely visible even through powerful telescopes. But when astronomers measured its mass, they stumbled upon a cosmic paradox. This dim wisp of a galaxy weighs as much as the Milky Way, yet emits less than 1% of the light. Where is all that missing mass? The answer rewrites the rules of how galaxies form. Dragonfly 44 is a dark galaxy, a celestial phantom where dark matter isn't just present, it's practically the only thing holding this cosmic enigma together. What makes Dragonfly 44 so revolutionary isn't just its darkness, but its defiance. Traditional galaxy formation hinges on stars, their gravity, their light, their ability to attract gas and dust to build structure. Here, stars are an afterthought, scattered like faint embers in a sea of unseen mass. Imagine a city where the buildings are invisible, their presence revealed only by the paths of the few streetlights floating untethered in the dark. That's Dragonfly 44, a galaxy where dark matter's gravity clutches a handful of stars so thinly spread you could fly between them for light years without seeing a single sun. The numbers are staggering. While the Milky Way boasts 200 billion stars, Dragonfly 44 has just 100 million, 1,000 times fewer, yet moves at velocities suggesting a gravitational grip equivalent to our own galaxy. The only explanation, a dark matter halo so dense it comprises 99.99% of the galaxy's mass. This isn't just a galaxy with dark matter. It's a dark matter structure that happens to have a few stars sprinkled in like cosmic garnish. How does something like this form? One theory suggests it's a failed galaxy, a place where normal matter was stripped away by violent encounters with neighboring galaxies, leaving behind a skeleton of dark matter. The Coma cluster, with its crowded gravitational dances, could have ripped away Dragonfly 44's gas and stars over billions of years, leaving only its dark framework intact. Another idea posits it formed differently from the start, emerging from a primordial cloud of dark matter that never gathered enough ordinary atoms to ignite prolific star birth. But Dragonfly 44's true significance lies in the questions it forces us to ask. If dark matter can assemble into structures this massive without stars, how many other dark galaxies are lurking unseen? Current surveys suggest there could be thousands, their absence of light making them nearly impossible to detect unless, like Dragonfly 44, they're caught in the gravitational backlight of a cluster. It's a humbling thought. We've mapped the universe's luminous cities, but might be missing entire shadow continents. Even more tantalizing is what this galaxy reveals about dark matter itself. The way its stars move suggests dark matter is cold, slow-moving and clumpy, exactly as predicted by leading cosmological models. If dark matter were warm or interacted strongly with itself, Dragonfly 44's halo would be smoother, its stars distributed differently. Instead, it's a near-perfect laboratory for testing theories about the invisible scaffolding of the cosmos. Yet mysteries remain. Why do the few stars in Dragonfly 44 orbit so slowly compared to the galaxy's immense dark matter halo? Some researchers speculate these stars might be newcomers, captured from passing galaxies rather than born in place. Others wonder if the dark matter here is arranged in an unusual configuration, like an invisible whirlpool shaping the paths of visible matter. One thing is certain, Dragonfly 44 is more than a curiosity. It's a window into the universe's hidden architecture. It shows us that dark matter isn't just a passive ingredient. It can take center stage, building structures where light barely dare tread. And as we peer deeper into the darkness, we're left to wonder, is this galaxy a cosmic fluke or the first glimpse of a parallel universe of shadow woven silently between the stars? Hanging like a tattered banner in the galactic wind, the Boötes Roman 3 stellar overdensity tells the story of a dwarf galaxy that dared to wander too close to the Milky Way's gravitational grasp. This faint smudge of stars, discovered in 2009, isn't just another satellite galaxy, it's a cosmic crime scene, the remnants of a stellar system ripped apart by tidal forces until only its ghostly skeleton remained. Stretching across 200 light-years, yet containing fewer stars than some globular clusters, Boötes Roman 3 is a study in contrasts, faint enough to blend into the background of the night sky, yet massive enough to hint at something lurking beneath the stellar surface. The secret to its heft, dark matter, and lots of it. Despite its sparse population of visible stars, measurements of their motions reveal this structure weighs at least 30,000 times more than the Sun. Ordinary matter can't account for that kind of mass, meaning Boötes Roman 3 is likely the corpse of a dark matter-dominated dwarf galaxy, its invisible halo still clinging to the stars it once cradled. Picture an iceberg where the tips, the visible stars, are just 1% of the whole. the rest hidden in the form of shadowy particles that refuse to interact with light. This makes Boötes Roman 3 a fossil record of galactic cannibalism, a snapshot of how the Milky Way grows by devouring smaller neighbors and absorbing their dark matter into its own halo. Yet the real intrigue lies in how this structure defies expectations. Unlike tidally disrupted streams like the Sagittarius stream, which form long, ribbon-like tails, Boötes Roman 3 remains oddly cohesive. Its stars move in a synchronized, almost orbital pattern, suggesting the galaxy's core might have survived relatively intact even as its outer layers were shredded. Some astronomers speculate this could mean Boötes Roman 3 was unusually dense before its collision, its dark matter packing enough gravitational punch to resist total disintegration. Others wonder if we're seeing it at a special moment caught mid-disruption, like a snowball slowly melting in the sun. Then there's the puzzle of its stars. The handful of suns we can observe in Boötes Roman 3 are ancient, nearly as old as the universe itself, and strikingly metal-poor, meaning they formed before later generations of stars could seed the cosmos with heavier elements. This paints a portrait of a galaxy frozen in time, a relic from the universe's early days that somehow avoided significant star formation before meeting its fate. It's like finding a prehistoric cave painting hidden in a modern city, a glimpse of a far older, simpler cosmos preserved by chance. What makes Boötes Roman 3 so valuable isn't just its history, but what it reveals about dark matter's role in galaxy formation. Simulations suggest the universe should be teeming with thousands of dwarf galaxies orbiting large spirals like the Milky Way, yet we've only found a few dozen. Could the rest be like Boötes Roman 3, so thoroughly stripped of stars that they're nearly invisible, detectable only by the gravitational fingerprints of their dark matter? If so, this cosmic ghost might be the key to unlocking one of astronomy's greatest missing persons cases, the hunt for the universe's shadow galaxies. As telescopes grow more sensitive to these faint, sprawling structures, we may find that Boötes Roman 3 is just the first of many, a pioneer in a new class of galactic archaeology where the most revealing fossils aren't made of stars, but of the invisible stuff that binds them. And in its tattered remains, we're reminded that even in destruction, the cosmos leaves clues, written in the orbits of lonely stars and the whispers of dark matter we're only beginning to hear. On August 15, 1977, a radio telescope in Ohio picked up something that would become one of the most tantalizing cosmic mysteries of all time, a signal so striking that the astronomer who discovered it scribbled, "Wow." In the margin of the printout, the wow signal lasted just 72 seconds, blasting a narrowband radio frequency, exactly matching the predicted signature of intelligent extraterrestrial transmission. Then, just as suddenly as it appeared, it vanished, never to be heard again. At first glance, the signal seemed to check all the boxes for an artificial broadcast. It was concentrated at 1420 MHz, a frequency shielded by international agreement from earthly interference because it's where hydrogen, the most common element in the universe, naturally emits radio waves. That makes it a logical cosmic hailing frequency any advanced civilization might use. The signal also followed a clear intensity curve, rising, peaking, then fading, just as you'd expect if it originated from a fixed point in space and the Earth's rotation swept the telescope's beam across it. It was as if the universe had whispered hello, then immediately hung up the phone. For decades, the leading natural explanation involved comets. In 2016, astronomer Antonio Paris suggested that two passing comets, 266P/Christensen and 335P/Gibbs, might have been the culprits. Their hydrogen-rich atmospheres could, in theory, emit radio waves at the right frequency as they neared the Sun. But skepticism quickly mounted. The comets weren't in the right part of the sky at the time, and no other comet has ever been observed producing such a powerful, focused burst. Even Paris later conceded the timing didn't quite add up. Then there's the extraterrestrial hypothesis. The signal originated near the Chi Sagittarii star group, a patch of sky with no known planets at the time. But recent exoplanet discoveries have shown that habitable worlds could exist around stars we once dismissed as unlikely hosts. If a civilization out there aimed a powerful beacon our way, even briefly, could we have intercepted a fleeting moment of contact? The signal's brevity might suggest a targeted transmission, not a continuous broadcast like a lighthouse beam sweeping past rather than a steady glow. Modern efforts to solve the mystery have only deepened the intrigue. In 2020, the Breakthrough Listen project scanned the same region with vastly more sensitive equipment, hunting for any whisper of a repeat. They found nothing. Meanwhile, alternative theories keep emerging. Some propose the signal was a reflected terrestrial broadcast, perhaps a military transmission bouncing off space debris, though no matching human signal has ever been identified. Others wonder if it was an artifact of an undiscovered astrophysical phenomenon, something that emits in narrow bursts we've yet to categorize. The WOW signal's legacy isn't just about what we heard, but what we didn't. Its silence since 1977 forces us to confront how little we truly know about the radio sky. It could have been a one-in-a-million cosmic fluke, a blip of interference, or something far more profound, a single, unanswerable question echoing across the light years. And until we catch another whisper like it, that question will linger. Were we almost not alone in the universe, or did we simply mishear the cosmos talking to itself? From the gravitational vortex of the Great Attractor to the ghostly radio whispers of odd radio circles, we've journeyed through 25 cosmic marvels that defy imagination. Each one, whether it's the diamond-studded corpse of a pulsar planet or the galaxy-sized void where nothingness reigns, challenges what we thought possible. These aren't just curiosities, they're cosmic rebellion where the universe gleefully scribbles outside the lines of every textbook. Consider how much we've learned, yet how much remains just beyond our grasp. The dark matter scaffolding of Dragonfly 44, the phantom pull of the dark flow, the mathematical defiance of the giant arc. These enigmas aren't roadblocks to understanding, but invitations to dig deeper. They prove that every answer we uncover plants the seeds for a dozen new questions. And isn't that exhilarating? The cosmos isn't a puzzle to be solved, but a conversation that never ends. Maybe that's the real magic here. These structures, some beautiful, some terrifying, all incomprehensibly vast, remind us that wonder isn't reserved for astronomers with billion-dollar telescopes. It's there for anyone who's ever looked up at the night sky and felt that tug of curiosity. So tell me, which of these cosmic rebels captured your imagination? Was it the eerie silence of the Boötes void, or the fiery defiance of the Phoenix Cluster's black hole? Drop your favorites in the comments, along with any wild theories you've got. After all, the next great cosmic revelation might start with a conversation right here. And who knows, the universe still has plenty of tricks up its sleeve. Maybe one day you'll be the one to spot the anomaly that rewrites the rules. Until then, keep looking up, because out there in the darkness between the stars, the next great mystery